Section 9.3, Principal Component Analysis, PCA. The PCA is a statistical procedure that uses an orthogonal transformation from possibly correlated variables into linearly uncorrelated variables. Such uncorrelated variables are called the principal components. They are orthogonal each other. The orthogonal axes can be interpreted as the direction of maximum variance under the condition that the new future axes are orthogonal to each other. See this figure. For this given data distribution, the maximum variance direction looks this one. So that is the first principal direction, and second one must be orthogonal. So we have second principal direction, so orthogonal each other. Technically, the PCA are highly sensitive to data scaling. We may have to standardize the entries of data metric before applying the PCA, particularly when the features were measured on different scales and we want to assign equal importance to all features. Okay, let's see this example. For the data metric, for example, one column, the entries, the value must be maybe order 1. For another column, the entry values can be order of 1 million. Then in this case, it's not easy to achieve equal importance for all features. This feature having large value will be considered more importantly, so that you may have to scale so that they are in the same scale or very meaningful scales. However, more important thing is here. Okay, let's see this kind of data distribution. Then apparently, the first principal direction must be like a vertical. However, if you are measuring the variance from the origin, then now everything is on the right side, so that once you try to work on this data set without any scaling, any translation, if you apply the PCA, then your first principal direction must be that direction. So the basic requirement is always you have to translate the data so that that center must be the origin, which means that for the data points, the average value must be subtracted, then it's automatically translated to the origin, right? That is required operation before using the PCA. But for other scaling, it is sensitive, so it can make some at a certain error. However, this lag of translating the origin will completely destroy your analysis. You have to do. Okay, computation of principal components. Consider a data metric X in n by d dimensions. Each the n rows represents a different data point. So in data metric, each row we stack horizontally, and each row is a data point, and data point has D features, so that each of the D columns gives us a particular kind of a feature, and each column has 0 empirical mean. I mentioned this one. This is really required. Our goal is to find an orthogonal wave metric. W is a square metric such that right multiplication maximize the variance. And this is orthogonal weight metric, so that each column of W will be orthogonal, and also in that that's called the score metric. Also, each column of score metric is also orthogonal. They are principal components of A. Let's begin with the first weight vector W1. Okay, now given data metric and W1, the first wave vector, then also left hand side, that will be Z1, the first principal component. And we want to maximize, in the beginning, we want to maximize the variance of Z1. Variance is simply 2 norm squared. We will try to find W such that now that is maximized. That is W1. And among possible W, we try to find the value maximized. And it can be written in this way because the norm squared is the same as, okay, this one is same as x w transpose and x w. So that once you apply transpose, then we can reach at that one. Now, rather than using norm is 1, we drop it, and then now for only non-zero and scale divided by W norm squared. Then they are the same. Now this is a Rayleigh quotient. For such a Rayleigh quotient, we have good theory, so we can use it. The purpose is to solve that problem, in fact this one. For positive semi-definite matrix, such as X transpose X, positive semi-definite, that means that eigenvalues are non-negative. If all eigenvalues are positive, then we say positive definite. But semi-definite means non-negative. For such metric, the maximum of the Rayleigh quotient, so X transpose X is a metric, so front back and given in this way. Now this quotient is the same as the largest eigenvalue of the metric, which occurs when W is the corresponding eigenvector. That means that now W1, so here W1 is scaled V1, which is the eigenvector corresponding to the largest eigenvalue. So after finding eigenvector for the largest eigenvalue and scale so that length 1, then that is exactly W1. This is how we can find the first wave vector. Basically, this wave vector will maximize the transformed data, the variance. Okay. How about the other weight vectors? Let's try to find the kth weight vector. And now from 1 to k minus 1, we assume we have already weight vectors. Then from original data set, we try to find the component and in the direction of now first potential component and second up to k minus 1, and we try to all component in data set for the prior principal directions. Then we define that as the remainder part is xk hat. For that xk hat, we'll try to find the weight vector which extract the maximum variance. So that after multiplying w and that norm is maximized them. So in this way, for remainder part, we try to find weight vector which maximizes the variance. So wk must be an eigenvector of x transpose x. So it is an eigenvector of x transpose x. So eventually, the weight vectors must be eigenvectors of x transpose x. Here we have a summary. The transformation matrix W is the stack of eigenvectors of x transpose x. X transpose x Wj is lambda j Wj, and now they are orthogonal each other, and of course length is 1. After scaling, we can get length 1. So that is stack of length 1 eigenvectors of A transpose A. That is exactly the weight metric. Of course, here the corresponding eigenvalue are decreasing. Once W is found, then data vector X is transformed to a d-dimensional row vector of principal components. And once W is multiplied, then there is a row vector. Okay, we have a remark. The principal components transformation is closely related with the singular value decomposition of X. Okay, we have the singular value decomposition of X, then U is left singular vectors, and sigma is the diagonal metric of singular values, and V is right singular vectors. Of course, sigma is written explicitly in this way, diagonal metric of sigma 1 to sigma d, and in decreasing order. Now, with that singular value decomposition, if we form X transpose A, then we have U transpose U, which must be identity, and now sigma squared. So we reach at thereon. This is eigenvalue decomposition. And once you have this decomposition, and of course this is a diagonal metric, then the diagonal entry must be eigenvalues of the metric, and columns of the metric V must be the corresponding eigenvectors in the same order, so that the right singular vector V, and in the singular value decomposition, is now eigenvectors of X transpose X. So that means that, and that means now V is almost same as W. In fact, essentially, they are the same. And right singular vector V is the eigenvectors of X transpose X. But earlier, we know that now that is the stack of eigenvectors. But this one is also the V in singular value decomposition. V is satisfying such equation so that we can say V is the same as W. The reason I'm using this in notation is that the vectors can have a different sign. And once it is an eigenvector, length 1, then -1 multiplication is again length 1 eigenvector. So that possibly some signs may be different. But except that, everything else must be the same. So we may say that they are the same. Also, the square of the singular value of X are equal to the eigen values of X transpose X. When we learn how to compute the singular value decomposition, and we try to find eigenvalue of that and then take a square root to find the singular value. So that is exactly this one. So we simply say W is V, ignoring the sign. Then, now Z is XW, and X is the singular value decomposition. So the Z becomes U sigma. So we may claim like this, while the weight matrix W is the collection of eigenvectors of X transpose X. The score matrix Z, that one, is now, once you multiply then sigma values will scale the columns of U. Okay. The score matrix Z is the stack of eigenvectors of X transpose. When we learn singular value decomposition, we already know that U, the columns of U are eigenvectors of X transpose and scaled by the square root of the eigenvalues. So that is exactly here. The Z is square root of lambda 1. Of course, that is sigma 1 and U1, and sigma 2, U2, and so on. Okay? Okay, and dimensionality reduction and data compression. In many applications, we don't have to keep all principal components, so that we may try to keep only the first K pieces, so only the first K principal components, then and that will make some approximation. And that is actually the idea of dimensionality reduction and or data compression. For example, rather than using whole weight matrix, we try to select only K columns of W. Then in square matrix, we'll have only K columns, so that dimension is shrunk from original D-dimensional space to K dimension. Sometimes dimension D is larger than 100, larger than 1000, but in some cases, and we can choose a very small K around 10, and we can get some good approximation. So that's the idea of data compression. Okay. Now, in data domain, now that is in fact given in this way. Now zk is X and WK and WK transpose. Okay? That is in data domain, this is approximation. Once you chop out and transformation and the related back transformation, then in the data domain, it is a kind of a, approximation. So let's try to measure the difference between original data metric and its approximation using only K components. Let's begin with the singular value decomposition. Then square metric Z is XW. So that is the same as U sigma. Okay. Now for that one, from this one, now truncated square metric ZK is XWK. We are using only K components. Okay, that is, now by using the singular value decomposition, we reach at that. But now, okay, and W is also a sort of a V, but only it is K columns, so that it's the same as, okay, this one is up to K component is identity and remainder part is 0. So that only the K component affect. So it looks like, and we are choosing only sigma K, only K components, because from here now, and first K component is identity, but remainder part is 0. Once it's multiplied, then it must be same as that. Sigma K is K singular values, and remainder part is 0. Okay, so we reach at this one. Now XK is ZK, now WK transpose. So ZK is U sigma K and WK transpose. Now it has already K components. So rather than K vectors, K columns, we may try to use whole weight metric. However, it's okay, and it's not changing anything because already sigma has only K components and remainder part is 0, so that although this one is expanded, it's not changing. So we reach out that one. So we reach this approximation. So simply, such truncated square metric and truncated the operation is the same as simply we are choosing K component from the diagonal sigma metric. That means only we are considering the singular values, or first K singular values. Okay. Now, what is the difference between X and XK in L2 norm? That is, by using singular value decomposition, we can write in this way. And then, now XK, already we know in this way. Okay, U, we can factor out. And then also V transpose, factor out. U and V transpose having the property so that, for example, U transpose U is identity. Once a metric has such property, then length must be preserved. Angle, dot product, everything must be preserved. We can easily see that. Okay, let's check it. U, X. Okay, there's norm squared. Let's begin with that one. That's same as U, X, transpose U, X. Then the same as X transpose U, X. This is identity, so that X transpose X, that is same as now X norm squared. So ux norm squared must be same as x norm squared, which means that in length computation, we may ignore such matrix. Once a matrix satisfies such property, then we can ignore. So we can ignore this one, we can ignore that one. So eventually we have that. Now, for this one, quite easy. Original sigma is a matrix, so that here there is a sigma 1, and some is sigma k, and go down, and sigma d. But the second one, sigma k, is from 0 over there all the way up here 0, and sigma k plus 1, go down sigma d. So once we subtract, then and sigma, oops, I'm sorry, I made this one wrong way for that one. Okay, let's try to eliminate here. Okay, sorry about that. Sigma k, first the sigma, okay, from sigma 1 to sigma k, and then from here 0, 0, 0, 0, right? Somehow I thought opposite way. So after subtraction, this will disappear, and first non-zero will be sigma k plus 1. For the subtraction, sigma k plus 1 is the largest eigenvalue, so that's the L2 norm. Okay, so we can easily compute the difference. Also, easy to approximate. Just choose first the k components from the singular metric sigma k, so that we can get approximation, and then also difference can be easily understood. So mostly singular values are rapidly decreasing. Largest single value, and then next one is going down very rapidly. So that if you are choosing here the k, then only consider k component, then you can see here now sigma k plus 1. If it is small, then that means the difference is very small. Right? So you can see quite easily how much you are ignoring. Okay. Efficient algorithms exist to calculate the singular value decomposition of x without having to form the metric x transpose x. And we considered this algorithm already. And computing the SVD is now the standard way to carry out the principal component analysis. That means that for the PCA, the SVD is the major tool. So without SVD, it'll be much more complicated. So the PCA is highly related with the singular value decomposition. Okay, this is the end of section and end of chapter. Thank you.